Hello students, today we will study some of the questions that is of exercise 1.1. This is the topic of standard 10 chapter number 1 real numbers. So let us study question number 4. And what is the question? Question is use Euclid's division lemma to show that the square of any positive integer is either of the form 3m or 3m plus 1. What is m? M is some integer, right? So what we have to show that the square of any positive integer. So let's start from the first number. So that we can write down square of positive integer as 1 square is 1, square of 2 is 4, square of 3 is 9 and square of 4 is 16. You can also write down other square numbers 25, 36, right? Okay. So let us suppose that x be any positive integer. We have taken x as any positive integer. That means the value of x is from 1 to infinite. X contain any value from 1 to infinite, right? So let the x be any positive integer and b is equals to 3. The value of b is equals to 3. Now what is b? B is the second integer that is stated in the Euclid's division lemma. Euclid's division lemma, what is Euclid's division lemma? That is a is equals to bq plus r, right? That you know now very well. So that value of b is equals to 3. Why we take the value of b is equals to 3? Why we not take b is equals to 2? Why we do not take y is equals to 4? Because in the question we have stated that in the hint that we can take the positive integer in the form of either 3q or 3q plus 1 or 3q plus 2. That is why according to the hint given in the question 3q is there. So what is in the multiple of q? That is b, and b is equals to 3. That is why we take b is equals to 3. Okay. Now we have to show that we have suppose let x be any positive integer and square of that positive integer is either in the form of 3m or 3m plus 1. And what is m? M is some integer. So now the question is clear. What we have to prove, that is clear. So let us now process for the proving that or to showing that we have to ask in the question. So now according to the condition of b and r, we can write down that the value of r, the remainder, is in between 0 and 3. R contains the value from 0 up to 3, but we cannot take 3. So the value of r, possible value of r, we can say that 0, 1 and 2, right? So what will happen if we take 0? Then our positive integer becomes 3q. Three possibilities are there. One is x is equals to 3q. Second possibility is 3q plus 1. And third possibility is 3q plus 2. So for all three possibilities, we have to do the square. Because we have to prove that the square of any positive integer is either in the form of 3m or 3m plus 1. So let us check one by one case. If we apply the square for the first possibilities, that is x is equals to 3q plus 0. It is actually 3q plus 0, but according to the addition of 0, we do not write it here. So what will happen if we apply the square both the side? By doing the square both the side, here we will get x square, here we will get 3q square, all square. So 3 square is 9 and q square is q square. So notice that the square of this is in the form of 9q square. Can we form it in the 3m form? What is here 3? So can we take one factor from this as a 3? Yes, because 3 is a factor of 9. So if we take 3 as a factor, other two factors remain is 3q square. So we do not write any another thing that you cannot understand. We just split this 9 into 3 multiplied by 3. So 9 is 3 multiplied by 3 and q square remains as it is. So we have write down this 3 outside the bracket, 3q square in the bracket. Why? Because now in place of this 3q square we can put down m. M is equals to 3q square. Why we put 3 instead of 3q square? Why we put m? Remember what we have given m as. M we can take as any positive integer. Then what is the value of 3q square here? Remember in Euclid's division lemma we have said that the two variables that we get r and b are also the positive integers. So this q has some kind of integer value. Let's suppose q is equals to 3 or 3. Let's suppose q is equals to 5. So what we will get here, q square, that is equals to 25. 25 3s are 75. So instead of this 3q square, which value we get? 75. So we can represent this 75 as a m, right? And m is also integer. 75 is also integer. We just represent this 3q square as m. So this 3q square is a positive integer, m is a positive integer, so that we can write down the square of any positive integer in the form of 3q. Clear? Understand? Okay. So in the same way, now we will study the second case. Second case is x is equals to 3q plus 1. Now applying the square both the side, here we will get x square, right hand side we will get 3q plus 1 whole square. Now if we have to apply here the identity, because the whole bracket square is there. So the square of first term is 9q square. Middle term will be 2 into first term into second term, that is we get 6q, and the square of second term, that is equals to 1. 1 square is 1. Now notice these two terms. From these two terms we can take 3 as a common. Yes. Then what will remain in the bracket? If we take 3 as a common, 3q square plus 2q will remain. And this plus 1 remains as it is outside the bracket. So now instead of this 3q square plus 2q, what we will get? As q is a positive integer, we will get some value of integer for this bracket, like say 100, 1000, 100, 2055, any value, but it must be a positive integer. So instead of this bracket we can put down one integer, that is m, right? So here we will get 3m plus 1. So we get the x square is equals to 3m plus 1. So this 3m plus 1 is the form of this. We have given the question that the square of any positive integer is either in the form of 3m or 3m plus 1. So the first case we get the square is equals to 3m form. For the second square we get the square in the 3m plus 1 form. Okay. Now let us study the third case. The same process we have to do. X is equals to 3q plus 2. By applying the square both the side, here we will get x square is equals to 3q square, that is 9q square. Middle term is 12q and the last term is square of 2, that is equals to 4. Now we can write down this 4 as an addition of 3 and 1. Why we do 3 and 1? That we will understand in the next step. We have write down 4 as a 3 plus 1. So now from all these terms we can take 3 as a common. By taking 3 as a common, what will remain in the bracket? Instead of 9q square we have 3q square. Instead of 12q we have 4q. Instead of these 3 we have 1. So the bracket is over. This 1 will remain, that we have write down separately as a plus 1. That is why now you understand why we split this 4 as 3 plus 1. Because By doing this, we can take 3 as a common from these 3 terms, right? So this 3 is common. This bracket we will get like this, and plus 1 remain as it is. Here also, instead of this bracket, what we will get? Some integer value, and instead of that integer value, we can write down one value, that is m, because m is also integer. This bracket is also some kind of integer. So we will get the square of positive integer in the form of 3m plus 1, and that we have to prove in the question. So here the sum is over. Again I have to say that whenever we have to prove the square as a 3m and 3m plus 1 form, we have to take the b as a 3, and that is why we get the 3 case, 3q plus 0, 3q plus 1 and 3q plus 2. Now applying both the side square, whatever we get is represented as either in the form of 3m or in the form of 3m plus 1. Right? So this is all about this sum. Okay? Okay, so let us study question number 5. And what is the question? Question is, use Euclid's division lemma to show that the cube of any positive integer is of the form 9m, 9m plus 1 or 9m plus 8. So here we have to use the cube of any positive integer. So we know that the cube of positive integers are like this: 1, 8, 27, 64, 125. Okay, so here we have to prove that the cube of, if we take a as a positive integer, then the cube of any positive integer is either in the form of 9m or 9m plus 1 or 9m plus 8. Now what will happen? From where we have to start? First of all, we have to check the possibilities for the positive integer a. To do that, we must have the value of b. But here you can notice that if we take 9 as a b, then we have how many cases? 9 cases we have. First case we have to use is 9m plus 0. Second case we have to take is 9m plus 1. Then 9m plus 2, 9m plus 3, 9m plus 4, up to 9m plus 8. So we have total 9 cases. And for all cases, we have to apply the cube. We have to apply the cube, and then we have to show that the cube of all the 9 cases is either in the form of 9m, 9m plus 1 or 9m plus 8. So this is a lengthy process. Instead of that, we can consider the same value that we have taken in the previous sum. That means if let a be any positive integer, and if we take b is equals to 3 instead of 9, then what will happen? We must have the value of r in between 0 and 3. So here the value of r is, for the 3 values of r we can get 0, 1 and 2. If we take 9 here, then we have 8 values. So that sum will be lengthy. Instead of that, we can take 3. Yes, we can take this value as a 3 because 3 is a multiple of 9. That is why we can take the value of b as a 3. Okay. So here also we have 3 cases. First one is a is equals to 3q plus 0, that I have not write down. 3q we can write down as it is because by adding 0 we get the same value. The second case we get is a is equals to 3q plus 1, and third case we get is a is equals to 3q plus 2. Now for all these 3 cases we have to apply the cube. By doing the cube in the first case, we get a cube is equals to whole 3q whole cube, and 3q whole cube we get as a 27q cube. Now notice the result that we have to get. 9 is there. Can we take 9 as a factor of 27q cube? Yes. By taking 9 as a factor, what will remain? 3q cube in the bracket. So this, instead of this 3q cube, what we can write down? M. Because 3q cube has some value that is a positive integer, and instead of this positive integer value, we can put down another positive integer, let's suppose m. So this we can write down as a 9m. So what we do, where instead of 3q cube we have taken as a m. Okay, both this value and this value both are positive integer, that is why we take m instead of 3q cube. So here you can notice that for the first case the cube of any positive integer is in the form of 9m, first form we get. Now apply the second case, this the same cube from both the sides, we will get a cube is equals to 3q plus 1 whole cube. Now a cube will remain as it is. We have to apply the identity of cube of two terms, right? Then what will happen? The cube of first term is 27q cube. Cube of 1 is 1. Now we get 3a square b. According to the identity, 3a square b, that is 3 square of first term into second term plus 3 square of second term into first term. By doing this we get 27q cube as it is. Now we will write down this 1 to the last. This 1 we have shifted to the last. Here also we get 3 square is 9, 9 3s are 27, q square. And here we get 3 3s are 9 into cube. Why we take this 1 to the last? Why we write down shift this 1 to the last? Because from all these three terms we can take 9 as a common. So by taking 9 as a common from this three term, we will get a cube is equals to 9 in the bracket 3q cube plus 3q square plus q, and this 1 remains as it is outside the bracket. So what is this 3q cube plus 3q square plus q? Some integer. So out instead of this bracket we can write down m, right? So this will become 9m plus 1. Cube of a positive integer a is in the form of 9m plus 1. So where what we do, instead of m, instead of 3q cube plus 3q square plus q, we put the value of m. Now you may have a question in the mind that why we do not take q as a common, because q is also there. We do not take q as a common because we have to find the answer, we have to represent the answer in the form of 3m plus 1. So according to the output we have to apply the input, right? That is why we process according to the output. By doing this and according to that, by that reason we do not take q as a common. Okay, so this is in the form of cube of positive integer is in the form of 9m plus 1. Now third case is 3q plus 2. Again by applying the cube both the side, here we will get the cube of first term, that is 27q cube. Cube of 2 is 8. Now according to this, 3 into square of first term into 2, total will become 54q square. Again the 3 in the bracket, 3q in the bracket, 2 square, that we get as a 36q. That you know now very well how to apply the cube, right? So here also this 8 we have to shift it to the right hand side at a last term, and out of this three term, first, second and this three term, we get 9 as a common. What will remain here? 3q cube. Here 6q square will remain. What will remain here? 4q, and this plus 8 remains as it is. Instead of this bracket, again what this bracket represent? This bracket represent any positive integer. Why? Because q is some kind of positive integer. So we put instead of q any value of positive integer. The total bracket will give us the integer only. So instead of this bracket we can simply put m. So this become 9m plus 8. So you can see that here for the third case also, cube of positive integer we get is in the form of 9m plus 8. 9m plus 8. So all the three cases we apply the cube and we get the result either in the form of 9m or 9m plus m plus 9m plus 8. So we can say that by doing the cube of any positive integer we get the value in the form of 9m or 9m plus 1 or 9m plus 8. Again you have one question in the mind your that how we can represent 1 in the form of this, either this or this. We can write down 1 cube in this form by taking the value of m is equals to 0. If we take m is equals to 0, this whole becomes 0, only 1 will remain. So 1 cube we get as a 1. Again, one question in your mind is that how we get cube 8? To do that, in this case, if we take m is equals to 0, then what will happen? This whole term becomes 0, only 8 will remain. So the cube of 2 we will get is 8. For 27, now you can think about that, how to get 27 out of these three cases, right? Here if we take m is equals to 3, then we get 9 3s are 27, and that is the cube of 3. Okay, so in this way you can think this question, the previous case question, and all this type of question you can think in your way and you can find your answer. Okay, so this is all about this lecture. Okay, thank you.